This is CAD Design Software's RF design capability demonstration. In our first section, we'll open up a pre-made schematic so we can generate a net list of the parts and part connections so we can make a physical layout. On initial startup of CAD Design Software, you'll be prompted to open up a technology file to start the design environment. For schematic, or to continue loading CAD Design Software, we'll just hit cancel. Now we'll open up our pre-made schematic. We'll open up the RF demo schematic drawing, which is located in the EPD sample RF subdirectory. We'll pick open. And from the CAD Design Software menu, we'll load the schematic environment. And we'll get a new menu, Schematic Capture. Now we can capture, we can build symbols, refer to libraries, place symbols and parts. And for this demonstration, we just want to capture the net list. So we'll go to Capture and we'll pick the Netlist command. And we'll get the Netlist Viewer dialog box. Right now is currently empty. We'll pick the Build button. The drawing will be analyzed and return the results of all the parts in the drawing and the nets as they are connected. Now that we have our net list, we'll pick the Save button to save it as a net file. We'll accept the default name of rfdemoschematic.net. We'll pick Save. And we'll be prompted that the netlist was now saved to the program files EPD sample RF subdirectory with the file name. We'll pick OK. We can also view the netlist by picking the Edit button, and it'll be opened up in the Notepad program. We can see how the EPD format netlist is viewed. We have a section of parts, and we have our section of nets. Additionally, in the schematic environment, these parts can be assigned widths for when they are read into the physical environment, such as using the track command. We'll identify the stored width from the net list and automatically make the trace or polyline the set width. We can close Notepad and we can exit out of the Netlist Viewer program. In our next section, we'll start the physical layout section. This is section 2 of the RF demonstration. After we've generated a net list of the parts and part connections from the schematic, we'll start a new drawing and we'll be prompted to read in a technology file. Now we'll read in the PCB 4-layer inch technology file and we'll pick Open. And this will set up our design environment with measurement units and a base set of layers to use throughout the design. We'll go ahead and save this. We'll save this in our RF. We'll save it as RF demo.dwg. Now we'll go into the technology. We can review the settings that is part of the PCB 4-layer inch. We have 4 layers in the design. We're using a layering sequence of near side to O2, O3 internal layers down to the far side layer. We have clearances that are preset for all of our entity clearances. And we'll go into layer types and we'll set up all of our layer types. Starting with the near side, we'll select type and we'll make this a mixed positive boundary plane. We'll set our O2 to a mixed positive plane. We'll set our O3 layer to a positive plane. And we'll set our far side to a mixed positive plane. I'll hold the Shift key and select all 4 layers, and I'll set a net name of G for ground, and I'll pick OK. and then we'll pick OK. And now we're set, and we'll pick the OK button once more, and now we're ready to start our design. Now that we've set up our environment, we need to create a boundary edge for the board to use. We're going to type PCB edge on the command line and press enter. We'll accept R for rectangle, press enter, and we'll set our size of 3.43 by 2.0, and we'll make that a corner base point. We'll also default to the layer PCB, which is the standard layer to place your outline boundary on. We'll pick OK, and now we have our board outline. Now that we have our board edge defined, we'll place some parts within the boundary edge. We'll go to the CAD Design Software, PCB menu, to the Parts, SMT, and we'll start with an SM chip. We'll select a preset from our parameter libraries. We'll use the code 1 0805. We'll pick Use Selected Code. And then we'll pick the Create and Block button so we can create and block the component into the design. You can manually place these, but for this tutorial we've provided coordinates. So we'll type those in now, 0.51, 1.43, and enter. 1.7, 1.43, and enter. 1.28, 0.90. 1.32, 0.77, and now we'll type R and enter to rotate the last placed part, and we'll type an angle of 90 and enter, and we'll place one more part, 1.855, 1.16, and enter. Then we'll press enter to exit the command, and now we have our components placed. As you can see now, the components have question marks, which means there are no reference designators assigned to these components. So we'll type REFDES for RefDes on the command line and press enter. And we'll start with the C1. We'll select the first component up here and its next component and the third. And as you can see, the RefDes command is upward sequencing the reference designators as each one is picked. For the two remaining parts, we need to assign these to an R, so we'll type C and enter to change, and we'll type R1 and enter, and we'll select our two parts. Then we can press enter to exit the RefDes command. We could type ZE and enter to zoom extents to see the board again. And now we'll parametrically create a part. We'll go to the CAD Design Software, RF menu, and we'll pick Radial S. In the block name, we'll type RAD1, and we'll pick the Edit Parameters button, and now we'll specify some parameters for this part. We'll 0.2 for the length, 120 for the angle, 0.05 for the conductor width, 0.05 for the conductor length. We'll pick OK, and then we'll pick Create and Block. And we have coordinates for this as well. We'll type 1.32, 1.02 and enter. And we'll press enter to exit the command. And we'll repeat our refdes command. And we'll assign a reference designator of EL1. We'll do one more RF component. We'll go back to the RF menu. I will select the coupler. We'll type in a block name of CP1, and then we'll pick the edit parameters, and we'll set up our values: 0.5, 0.02, 0.05 for the transmission line width, 0.03 for the W1 line width and 0.02 for the W2 line width. We'll pick OK. Then we'll pick the Create and Block button, and then we'll type in some coordinates, 2.13, 1.43, and enter. And then enter to exit the command. We'll repeat our refdes command, and we'll assign it a reference designator of CP1. Now I'll place the rest of the parts. Now that the basic parts from the parameter libraries were placed manually, we'll use CAD Design Software's place command to continue loading the remaining parts from the visual libraries. First, we'll set up our grid and snap. We'll go to the Tools, Drafting Settings. We'll turn our snap on, and we'll put in a value of 0.05. We'll turn on our grid, same value, 0.05. Pick OK. And now we'll go to the PCB Net menu, and we'll pick the Place command. We'll be prompted to load blocks from the libraries. We'll type Y and enter for yes. And we'll use the schematic netlist that was generated from the schematic earlier in the demo. Pick Open. Parts will be read into the drawing. And all the parts were found in the visual libraries in CAD Design Software. We'll first start by placing the two SMA parts. We'll select them from the Select Parts to Place list, and we'll pick the Place button. Now we're ready to place our component. We could type in the coordinates to place. Type in 0.2, 1.43, and enter. And we're done placing that part. So we'll press enter to go to the next part that was selected. And now it brings up reference to block SMA v Nearside. As you can see, the rat lines are currently being drawn because the netlist was read in, and the rat lines will always stay connected. We'll type in our value of 3.23, 1.43, and enter. And then we'll press enter to return back to the place command. And now we can place the remaining parts. We'll pick select all, and we'll pick place. I'll go ahead and pause the video so I can enter all these parts coordinately. Now I've finished placing all my parts. I'll press enter, and then I'll receive a message that all the components are now inserted from the place command. Pick OK, and now we're out of the command. Next, we'll use CAD Design Software's rat command to color some of our rats by their nets. We'll go to the PCB Net menu, and we'll pick the rat command. We'll get a warning box that nets have been added, and this is fine because this is because of all the parts that have been placed and the netlist that was read in. And we'll say yes to turn them on. Then we'll see all of our connections listed in the large scroll list here. We'll color our ground net to a green, and we'll pick our Power 5V net, and we'll color that to a red. And we'll pick the Draw Rats button, and now we can identify the connections by color. As an optional tool, after your parts have been placed and the rat lines have been connected, you may need to adjust some of the parts during the design. There's a command called DynaRat that will allow you to pick components and move them dynamically. For example, we'll pick this part over here. We'll get prompted to move or rotate. We'll type R. Then we could rotate the part. As you can see, the rat lines will follow. Hit escape to select another part. And if we type M to move, I'll hit escape. I'll just press enter to exit the command. Next, we'll need to define a via in the drawing so we can use that during routing when we need to route to other layers. We'll go to the PCB Route menu and we'll select Via. We'll have a prompt down here to go ahead and insert the default via. We'll type D and enter to define. In our whole edit box, we'll type in a value of 0.025. In our pad, we'll type in a value of 0.05. We'll make sure that the layering is going from the near side down all the way to the far side, and we'll pick OK. Now we just need to place this in the drawing, so we'll place it just outside the border here, and we'll press enter to exit the command. The via's block definition is now a footprint resident in the drawing. So when we need to pull out a via during the routing stage, this block will be ready. We can erase this at this point. Zoom extents. And now we're ready to start routing these rat lines into conductive traces. Next, we're ready to route the near side of the design. We'll go to PCB Route and we'll pick the track command. We'll type C and enter to configure. We'll disable our layer pairing, and we'll turn on our clearance checking on plus terminate feature, which will check for clearance once we press T to terminate the connection. We'll click OK. Then we'll zoom into the area between J1 and C1. We'll pick closer to C1, the surface mounted part, and not the through hole part. And then we could type T to terminate the connection. We can continue picking a rat line. As you can see, the clearance envelope has been shown around to avoid any clearance contacts or errors. We'll press T. Then we'll just go around to the rest of the design and pick some of these traces and press T. The terminate command in track will find the best route using 45-degree angles that were set in the track dialog box. We'll just continue to pick these rat lines. And we're pressing T to terminate them. And it creates the conductive trace from the rat line connection. We'll zoom in a little closer so we can grab our rat lines. And we'll keep pressing T. We'll grab our rat line from A1 down to R6, and we'll drag this down closer to R6, and then press T to terminate. We'll come over to our parts U1 and J4. What we're going to do is pick the rat line. We'll press U to undo. Closer on here to J3. We'll zoom out a little. We'll bring this down till the rat line is just about even, and then we'll press T to terminate. We'll do the same for pin 4. We'll route down and out. Looks about even. We'll press T. And we can press enter to exit the track command and zoom extents to see our design at this stage. Next, we'll do some far side and multi-layer routing with vias. Now we're ready to route on the far side and the internal layers using vias. We'll go to our PCB Route menu. We'll pick the track command. Then we'll type C and enter to configure track. In our layer pairing area, we'll select Enable, and we'll set our layer pairing to go from the trace near side to the trace O2 internal layer. Then we'll pick OK. And we'll zoom into our two parts over here. And we'll pick the rat line coming from pin 4, and we'll drag it down about even. About halfway, Then we'll type L to change the layer. Since our layer pairing was set to trace 02, it's asking us to place a via. We'll use our defined 0205 via and pick OK. Now you can see in the information corner L equals trace 02, which means now we are routing on the trace layer 02. Now we can type T to just terminate the connection, and the route is now complete. We'll repeat the process off of pin 4. We'll pick, add a point, type L. It'll insert the last place via, and then T to terminate. Now we'll type C and enter to configure. And we're going to our control area and we'll set net names to vias. Checkbox. We'll pick OK. We're going to grab the rat line from pin 1. We're going to drag this out about so far. Pick a point. We'll type L to add the via. Then we'll right click and we'll pick complete. We'll repeat the process. L, right click, and complete. We can press enter to exit our track command. We can type FM to turn off fill mode, as we can see our artwork now. As you can see, the via was placed. Now we'll do some additional routing. We'll zoom into the area of the A1 component. We'll run our track command again. We could type it in and press enter. We'll type C and enter to configure. We'll turn off the set net names to vias. And we'll set our layer pairing to go from trace near side to the trace far side, which is the back side of the board. And we'll pick OK. We'll pick our rat line from C2, and as we drag it closer to A1, since it is part of the same net, the rat line will jump to the component. So as soon as the rat line jumps to the next component in the net, we can type T to terminate. Then we'll grab the rat line from the L1 part, we'll right click, and we'll set our width to a value of 0.01. We'll pick auto dismiss. We'll come up and we'll type T to terminate. Pick our rat line from EL1 to a point. We'll type L to change our layer. We'll press undo. Go back in, press undo again. Type C. We'll set our via to multiple so we can select our via. We'll pick OK. And then we'll continue routing. Type L. And we want to select our smaller via, our 0204. And we'll pick OK. And now we're routing on the far side as indicated in the information corner. And we'll type T to terminate. We'll zoom into our component of U1. We're going to need to route this pin 1 over to Q1 pin 3. So we'll pick the rat line closer to the pad. We'll route up a bit. We'll type L to change our layer. We'll use our 0204 via. Now we're routing on the far side. We could pick a point and type T to terminate. We'll move over to our J3 component. We need to continue this last route right here from J3. So we'll zoom in and we'll pick our rat. Pick about midpoint. The program won't be able to clear the pads and give us an indication in the upper corner about an error to the terminal. So we'll type U to back up or U to undo. Now we can route through the two pads. I'll type U. Get that about even. Type T to terminate. Pick the rat line from R4, pin 1. We'll pick a point here. We'll type L, and we'll use our 0205 via. Then we can route down and through on the far side. Type L. We'll use our 0205 via once more. Now we can type T to terminate. You can press enter to exit the track command. Turn our fill mode on. Take a look at our design. Type ZE for zoom extents. And then in our next section, we'll route the final 2 rat lines with a differential pair. Next, we'll do some differential pair routing. We'll go back to our track command in route, and we'll type C and enter to configure. In the control area, we'll select Join to Existing Traces checkbox. In our differential pair area, we'll set our trace width to 0.015 and our trace gap to 0.008. We'll pick OK. Then we'll zoom into the parts between U1 and J4. And on the command line, we'll type D and enter for differential pair. We'll select our first and second rats. Now that we have both rats together, we'll start to pick points to route them together. When we're close to the end, we'll right click and pick complete. Now we can finish off the traces. Type T to terminate. And we can press enter to exit the track command. I'm going to type S and enter for the stretch command, and I'll just stretch my traces over a little to adjust and center them. And press enter. And now we have our differential pair routed. Next, we'll create a complex RF shape in the design. We'll zoom into the area between A1 and C2. We'll type V and enter for our vertex command, and I. We'll select a couple insertion points here. Press enter. We'll type B and enter to break these new vertices. Press enter and enter once more. Then we'll go to our PCB post-process and pick the PCB L-type command. We'll pick the SComp type for lines, square outside corners. Pick OK. And we'll select our new polyline and press enter. We'll set our current working layer to trace nearside. And now we'll go to our CAD Design Software, Software Utilities, Edge Solid. We'll pick the trace convert command. We'll select SComp. We'll select our polyline, and now we have an independent shape. We'll go back to the PCB post-process, PCB L-type command, and we'll select the enable circles at 0 width polyline vertices. We'll select the layers that we want these circles to show up on. These circles will allow us to see 0 width entities. As you can see, the corners are already showing the circles. So now we'll type V and enter to repeat the vertex command. And we'll type I and enter. We'll make sure our snap is on. And we'll place 6 new vertices on our shape. We'll press enter. I'll press M and enter to move, and we'll move these to start forming a new shape. Let's drag points out. Make sure our snap is staying on. Then we could press enter. We can press enter once more to exit the vertex command. Now that we're done with the shape, we could turn off the circles, the PCB type. We'll uncheck the enable checkbox and pick OK. And now we have our RF shape. Next we'll do trace tuning to set a specific length to our traces. We'll zoom into the area between U1 and J4. We'll go to our CAD Design Software, Software Utilities, Advanced Route menu, and we'll pick our Add Tune command. We'll set our values. 0.01, we'll accept the defaults, and we'll pick OK. We'll pick the polyline segment about here. We'll pick our center point, and our direction is downward. We'll repeat over here, center point, in a downward direction. Press enter to exit the command. Go back to Software Utilities, Advanced Route, and we'll pick our Tune 1 command. And we'll pick all of the parallel polyline segments. 1, 2, 3, and 4. Press enter. That allows us to tune the entire net. We'll press enter to say yes. We'll accept the fuzz factor default of 0.002. Then it'll ask us to enter length. We'll enter a length of 2.6 and enter. And now our traces are tuned. We'll return to the Software Utilities Advanced Route, and we'll pick the Tune 2 command. We'll pick this outer polyline segment. Press enter to tune the entire net, and enter to accept the default fuzz factor. And for our new length, we'll type in a value of 2.625. And we added an additional length to that polyline segment. Next we'll use the Tune 3 command to add a trombone tune. We'll pick a point on this upper polyline, right about in the middle here. We'll set our gap value to 0.01 and our chamfer distance to 0.005. We'll tune our entire net. We'll set our fuzz factor to 0.2, and then we'll pick OK. We'll type in a new length that we want is 2.625 and enter. And we can press enter once again to exit the command. Finally, we'll add a chamfer to the corner of this trace. We'll type FM and enter to turn off our fill mode. We'll go to the Software Utilities, Advanced Route, and we'll pick T-chamfer. We'll accept the defaults of an unfilled and a fuzz factor of 1.17 and pick OK. And we'll pick the vertex and we'll create the miter corner. Next, we'll create connections for all of our ground pins. We'll go to the PCB ground menu, and we'll pick the tie via command. In the slide window, we'll turn on all 4 ties. In our select by net name area, we'll pick the select nets, and we'll select the G ground net, and we'll pick OK. And then we'll pick the place ties on select nets button, and all the ties will be automatically placed. We'll go ahead and remove a few that were unnecessary. And all the ties are done. Next, we'll add ground ties to our through-hole parts. We'll go to the ground menu, and we'll pick the G tie command, and we'll set some values. In our air gap to pad edit box, we'll put in a value of 0.025, as well as in the air gap to hole. We'll set our rotation to 45 degrees. In our layers area, we'll pick select. We'll pick all of our tie layers on all of our layers, our far side and 2 internal layers, and we'll add those to the list so we can draw all the ties at once. In automatic features, we'll select the DRC checkbox, and we'll select the remove ties to eliminate DRC errors. Then we'll select the select nets button, and we're going to set this all to the ground net and pick OK. And then we'll place the ties on the selected nets. Now we can see that all the ties were drawn. If we go to our LX command and look at the art far side, we can see the ties there. LX T3, LX T2, and LX TN. As you can see on the trace near side, the ties were eliminated to avoid a DRC clearance error with the near side trace. Next, we'll set up the design to do a positive pour. First, we'll run our LX command, and we'll run trace near side to see all the artwork that will need to be poured. We'll go to the PCB ground menu, and we'll pick GND edge, and we'll set some values here of 0.015 for the air gap and 0.0 for our edge width. Our layer will default to ground edge near side. We'll pick OK. Ask us to pick the PCB edge. We'll pick the boundary on the PCB layer, and the ground edge will be drawn. Now we'll type LX AN for our artwork near side. And now we're ready to run a copper pour. We'll go to the PCB ground, and we'll pick the pour command. We'll set all of our air gap parameters to 0.015. In our field control area, we're going to do a positive boundary. We'll set our minimum plane width, edit box, to 0.01. We'll set our hatch scale edit box to 0.2. And we'll set our corner radius to 0.005. We'll enable progressive filleting for our edges. We'll set our increment to a value of 0.001, and our final radius to a value of 0.015. We'll set our angle of hatch to 45 degrees. Now we'll go assign some air gaps to our entities in the drawing. We'll pick the Assign Gaps button, and we'll zoom in on one of our couplers here. We'll select these two entities right here and press Enter. And we'll assign that an air gap of 0.05. Pick the Assign Gap and select Next Entities button. Now we'll type N and Enter to do entire nets at a time. We'll go around and we'll select all of the entities in nets. We'll just select all of these properties. We'll press Enter. We'll assign all of these an air gap of 0.05. We'll assign gap. Then we'll select these lands here, and this one, and this one. Press Enter. We'll set that to Ignore. And we'll assign the gap and exit. And now we're ready to pour. We'll pick the Pour button. We'll zoom out a little bit, and we'll pick our ground edge outline. Now the program is filleting all of the corners around these edges here. We can see the progress of the progressive filleting. And now the pour is done. We'll turn off our grid. Take a look around. As you can see, we have a few copper islands here, but we'll eliminate those a little later. And there's the near side pour. We'll also need to create pours for all the internal layers and the far side layer. We'll do another one. We'll do an LX A2. We'll turn on our PCB layer. We'll run our ground edge command. We'll set these values to 0.02 and 0.02 and pick OK and pick the outline. And we'll run the pour command. It'll ask us to turn the PCB layer off. We'll say yes. We'll do a positive fill, and we'll assign gaps. And we'll zoom into the lane coupler, and we'll select the three entities. We'll press Enter. We'll assign that a gap of 0.05. And we'll assign gap and select Next Entities. And we'll type N and Enter for the entire net. And we'll pick the polyline at EL2. And we'll also grab EL24. And press Enter. We'll assign that a gap of 0.05. And we'll assign the gap and exit. And then we'll run the pour. And there's our trace O2 copper boundary. Now I'll pause the video and pour the remaining O3 and far side layers. Okay, all of our layers are now poured. We'll use our LX command to see our artwork on the near side, on the O2 layer, O3 layer, and our far side layer. Next, we'll finish the ground plane by placing ground views everywhere the space is available. First, we'll do an LX, trace near side. Then we'll go to our PCB ground menu and we'll pick Pepper. We'll use the O2, O4 via. Make sure our net name is set to G. And our DRC distance, we'll set 0.05. And we'll select the Suppress Under Components checkbox. And then we'll pick the Create button. Now the Pepper command will pepper the entire surface to the PCB boundary edge, clear all the DRCs, and place the vias as needed. Next, we'll do a net check on the design and compare it to our original net list. We'll go to the PCB net menu and we'll pick net check. In the net names and capture net list area, we'll select the use via net names checkbox. In the shape base capture, we'll select check plane continuity and capture full copper. In the plane nets, we'll set that G as the default. Then we'll pick the Capture PCB Netlist button. The drawing will be analyzed. Information will be when the capture is done, we'll pick the Compare PCB Netlist button. And we'll use our rfdemo.net netlist. Pick Open. Now the program will compare the two netlists to each other and come up with any errors. We'll pick the Analyze Errors button, and we can see we have just a few errors. We have a D error for redundant trace. We could double click on that, and that's an acceptable error. We'll press Enter to return. On our islands, we know we have some copper islands. So we'll pick on those and we'll zoom to the error. Then we'll be prompted on the command line to delete accept or no action. We'll type D and enter to delete the copper island. Then we'll return to our net check command. We'll go to our next island and zoom to that error. And we'll type D and enter to delete. We'll run our net check command again. And we'll select the last island to remove. Type D and enter. And now we can just pick OK since the rest of the errors are acceptable. Turn all of our layers on. And now we're ready to do a design rule check. Next, we'll run a DRC on the design to check for any clearance errors. We'll go to PCB, check, and we'll pick DRC. Pick the Set Clearances button, and we're not running any special classes or anything on this design, so we'll just pick Set. And then we'll pick standard objects from both columns. We'll specify our clearance of 0.01, and we'll set that specified value. Then we'll select ground edge and ground plane and standard objects, and we'll set that clearance to 0.015. Okay, and then we'll pick OK, and OK once more. And we'll pick the Run DRC button, and then we'll window the entire drawing to check for all clearance errors. I'll press Enter. I'll go ahead and pause the video to save a little time. When the DRC is done checking the design, we'll get a result. In this case, there were no DRC errors found, so we'll pick OK. If there were DRC errors, we could type VE and enter, and the errors would be listed in this dialog box. We could double pick them to zoom to, fix the errors, run DRC again, and see if the clearances pass. Next, we'll create the fabrication and mask artwork. We'll go to the PCB, post-process, and we'll pick Table PC. We'll uncheck the Write Drill File checkbox. We'll set our size to 1.3 and our table text to 0.05. Then we'll pick OK. Then we'll assign some symbols to our holes in the drawing. You see we have 4. So I'll pick this button. I'll select symbol 5. I'll select symbol 6. Symbol 7. Then symbol 11. Then we'll pick OK. And it'll ask us to insert the whole table in the drawing. We'll zoom out a little bit. The whole table will be drawn, and all the holes will be placed for their symbols. Now we can look at this by using our LX command. Type LX and FB. We can see our fabrication layer. Next, we'll run the masks command to create masks for our solder paste and solder mask. We'll go to the PCB part edit, and we'll pick the masks command. We'll select solder mask. We'll set that to a value of 0.005. We'll set a solder paste mask and set that value to a negative 0.002. Then we'll pick OK. Then we can use our LX command and type MN for our mask near side, LX MF for our mask on the far side, LX PN for the solder paste, and LX TN. Next, we'll create an assembly drawing from our finished artwork. We'll go to the PCB post-process menu. We'll pick the Make ASY command. We'll set our reference designated text size to 0.04. We'll make sure that's top, and we'll set that to the near side. We'll pick OK, and the assembly drawing will be created. And now we can see our assembly drawing. Next, we'll create the silk screens for all the components. We'll go to PCB, post-process. We'll pick the silk move command. In our text angle, we'll set to 0 or 90 degrees only. In the existing text, we'll set that to always calculate new position. In the layers to process, we'll make sure that we only have near side selected. In the distances area, we'll set our clearance to other silk screen and component outlines of 0.01. And our maximum distance to component, we'll set that to 0.05. In our preferred locations, in our vertical components, we'll set the left pop-up list to 1, and we'll set our right to 2. In the text size area, we'll set our preferred to 0.04. Our minimum will be set to 0.03, and our increment will be set to 0.005. We'll pick the Move Designators button, and the drawing will create the silk screens for all the components. When the command is done, we can see the artwork by using our LX command. We'll type MN or SN. We can move the designators by grabbing by the grips and repositioning. And there we have our silk screens and designators. Finally, we're ready to output our design to Gerber. We'll go to CAD Design Software, Conversion menu, Gerber AirX, we'll pick the Gerber Out command. We'll pick the Automatic Setup button, and we'll purge all of our unused layers. Okay. We can review all of our settings, shows all of our layers, all of the layers that will be processed, and the file extension for all of our photoplot files. We'll pick OK. In our subbatches area, we'll now have all our subbatches that we'll be outputting. We can pick on each one and edit. We'll pick the trace near side, and we'll pick the settings for selected layer. In the activate area, we'll select fill control, and we'll set the polygon fill allow maximized and fill all. And we'll pick OK. And we'll pick OK. And we'll pick OK once more in our subbatch editor. And now we're ready to convert. We'll pick the Convert button and pick OK. We can review our Gerber output to see if there were any errors. Nice clean report. Now we can go use our Gerber View command to view all of our outputted Gerber. To view our Gerber files using the Gerber View command, we'll start a new session of CAD Design Software. We'll go to File, New, and we'll press Enter to accept the default template. We'll pick Cancel because we don't need a technology file. Then we'll go to the CAD Design Software, Conversion, Gerber AirX menu, and we'll pick Gerber View. We'll select our master aperture file, which is in our RF directory. We'll pick Open, and then we'll pick the View button. We can repeat our Gerber View command. We select each layer and isolate. Our trace far side. Our O3 layer. O2. We can also assign a color by double picking. We can set this to a lighter shade of blue. Our silkscreen layer, and our hole and fabrication. This concludes the RF design video demonstration.